Hello everyone. In this video we are going to learn the topic partial differentiation in the subject of Applied Mathematics 1. For this the prerequisites are the functions of two or more variables. We say if the mapping Z has one definite value for each pair of values of x and y, then Z is called a function of two variables, say x and y. We denote it by z is equal to f of x comma y, where z is the dependent variable and x and y are the independent variables. For example, z is equal to x square plus 2xy plus y square is the example of two variable function x and y. Now let us see the notations. For the ordinary derivative of z with respect to x of order say 1, 2 up to n, the notations are dz by dx, d2z by dx square, or dnz by dx raised to n. In case of partial derivative of z with respect to x of first order, we denote it by dabba z by dabba x or simply zx. In case of partial derivative of z of second order, if we denote z by f of x comma y, then partial derivative of dabba f by dabba x with respect to x is denoted by dabba 2f by dabba x square or simply fxx. Or if dabba f by dabba x is differentiated partially with respect to y, then it is denoted by dabba 2f by dabba x dabba y or simply fxy. Similarly, if dabba f by dabba y is partially differentiated with respect to x, it is denoted by dabba 2f by dabba y dabba x or simply fyx. Similarly, if dabba f by dabba y is redifferentiated with respect to y, it is denoted by dabba 2f by dabba y square or fyy. Now let us see the definition for partial derivative. The partial derivative of z is equal to f of x comma y with respect to x is the ordinary derivative of z with respect to x, treating y as a constant. It is denoted by dabba z by dabba x or zx. Similarly, partial derivative of z with respect to y is the ordinary derivative of z with respect to y, treating x as constant. It is denoted by dabba z by dabba y or simply zy. For example, if z is equal to x raised to y plus y raised to x, then we have to prove that dabba 2z by dabba x dabba y is equal to dabba 2z by dabba y dabba x. Let us see the solution. We are given z is equal to x raised to y plus y raised to x. First we calculate dabba z by dabba x, that is we differentiate partially z with respect to x. We get it is equal to y x raised to y minus 1 plus y raised to x log y. Now redifferentiating dabba z by dabba x with respect to y, we get dabba 2z by dabba x dabba y is equal to x raised to y minus 1 plus y x raised to y minus 1 log x plus x y raised to x minus 1 log y plus y x raised to y raised to x minus 1. We denote this as equation number 1. Similarly, we find what is dabba z by dabba y and we differentiate dabba z by dabba y with respect to x. We get this. We label this equation as equation number 2. Comparing equation number 1 and 2, both RHSs of 1 and 2 are similar, therefore LHSs of equation number 1 and 2 has to be similar. Therefore we say dabba 2z by dabba x dabba y is equal to dabba 2z by dabba y dabba x. Now look at the example number 2. It is similar to example number 1. I just changed the function. Here function is u is equal to log of x square plus y square. U is a function of x and y here. Here we have to prove dabba 2u by dabba x dabba y is equal to dabba 2u by dabba y dabba x. Let us see the solution part. Given u is equal to log of x square plus y square, differentiating u partially with respect to x, we get w by x is equal to 1 by x square plus y square into 2x, that is 2x upon x square plus y square. Now differentiating w by x partially with respect to y, we get w2u by x y is equal to minus 4xy whole divided by x square plus y square the whole square. We label this as equation number 1. Now differentiating u with respect to y, we get w by y, and differentiating w by y with respect to x, we get w2u by y x. We label this answer as equation number 2. Observe equation number 1 and 2. Their RHS are same, therefore LHS has to be same. Therefore from equation 1 and 2 we say w2u by x y is equal to w2u by y x. Now these are the practice examples that you can solve on the similar lines of example number 1 and 2. Now let us see what are composite functions. If z is a function of u and u is again a function of two variables x and y, then z becomes a composite function of x and y. Look at this tree diagram. You can see that z is a function of u and u is again a function of two variables. Therefore z becomes the composite function of two variables x and y. Now let us understand how to differentiate composite function. When we say that z is a function of x and y, as it is a function of two variables, its differentiation with respect to x or y is partial, and when we say that z is a function of u as a function of one variable, its differentiation with respect to u is ordinary. If z is not explicitly given in terms of x, then we have to use the chain rule, and therefore z by x is given by dz by du into w by x. As u is a function of x and y, its differentiation with respect to x is ordinary, therefore we denote it by w by x. Once again, differentiation of z partially with respect to x can be given by a chain rule, dz by du into w by x. On the similar lines, we can differentiate z partially with respect to y and is given by dz by du into w by y. Now let us understand the total differentiation. If u is a function of x and y are itself functions of t, then the total derivative of u is given by du by dt is equal to w by x into dx by dt plus w by y into dy by dt. You can see the similar thing in a tree diagram. U is a function of x and y are itself functions of t, therefore u becomes a function of t, therefore its differentiation with respect to t is the ordinary. But when we differentiate u with respect to x or y, its differentiation is partial. Similarly, when we say that x and y are functions of t, as they are functions of only one variable, their differentiation with respect to t is partial. It reflects in the formula of du by dt. By chain rule, it is given by w by x into dx by dt plus w by y into dy by dt. Now let us see this example. If z is equal to xy square plus x square y and x is equal to 80 square and y is equal to 280, then we have to find dz by dt. You can clearly observe that z is a function of two variables x and y are itself functions of t. Now we have to find out what is dz by dt. We first draw this tree diagram for the sake of writing a formula of dz by dt. So we know that dz by dt is equal to w by x into dx by dt plus dabba z by dabba y into dy by dt. Now we will substitute values for dabba z by dabba x. It is y square plus 2xy. Dx by dt is 2at. Dabba z by dabba y is 2xy plus x square, and dy by dt is 2a. Now substituting for y and x, we get dz by dt is this. More simplification will give you this. So the final answer dz by dt is equal to 4a square t square plus 4a square t cube into 2at plus 4a square t cube plus a square t raised to 4 is equal to 2a. Now let us go for example number 2. It is similar to previous example. Here z is given as e raised to xy, x is equal to t cos t, y is equal to t sin t, and we have to find dz by dt at a particular value of t pi by 2. Look at the solution part. Before proceeding, we draw a tree diagram. Here you can clearly see that z is a function of x and y are functions of t. Using this tree diagram, we can note down this formula: dz by dt is equal to dabba z by dabba x into dx by dt plus dabba z by dabba y into dy by dt. Now we will substitute values for the RHS entries. Dabba z by dabba x into dx by dt is given by y e raised to xy into cos t minus t sin t, and d dabba z by dabba y is given by x e raised to xy, where dy by dt is sin t plus t cos t. Now substituting for values of x and y, we get dz by dt is equal to t sin t e raised to t square cos t sin t into cos t minus t sin t plus t cos t e raised to t square cos t sin t into sin t plus t cos t. For t is equal to pi by 2, dz by dt becomes minus pi square by 4. Now we'll go for example number 3. This example is slightly different than example number 1 and 2. Here u is not explicitly given as a function of x, y and z. Instead it is defined as function of e raised to y minus z, e raised to z minus x and e raised to x minus y. Now we have to show that addition of partial derivatives of u is equal to 0. Now let us see the solution. Here we let p as e raised to y minus z, q as e raised to z minus x and r as e raised to x minus y, because of which u becomes now function of p, q and r. Now we can draw this tree diagram where you can see u is a function of p, q and r, and p, q, r are itself functions of x, y, z. Therefore we can write this formula for dabba u by dabba x. It is dabba u by dabba p into dabba p by dabba x plus dabba u by dabba q into dabba q by dabba x plus dabba u by dabba r into dabba r by dabba x. As u is not explicitly given in terms of p, q, r, we cannot find out what is dabba u by dabba p, dabba u by dabba q and dabba u by dabba r. But p, q and r explicitly given in terms of x, y, z, therefore we can find their partial derivatives with respect to x, y and z. Substituting values for dabba p by dabba x, dabba q by dabba x and dabba r by dabba x in this RHS part, we get this. We label this as equation number 1. On the similar lines, one can find out what is dabba u by dabba y. We label this as equation number 2. Similarly, we find what is dabba u by dabba z. We label this as equation number 3. When we add dabba u by dabba x, dabba u by dabba y and dabba u by dabba z, you see that the addition of RHSs of equation number 1, 2 and 3 becomes 0. Therefore we write adding equation 1, 2 and 3, ux plus uy plus uz becomes 0. These are some practice examples that you can try at home. Now let us see what are two variable implicit functions. It is a function in which the dependent variable is not isolated on one side of the equation, or simply these functions are not explicitly defined. Or when we say f of x comma y is equal to 0 and y is a function of x, then y is called as implicit function of x. For example, in the equation x square plus 2xy plus y square equal to 0, you can consider y as a function of x. Therefore, y is implicit function of x. Now let us see how to differentiate implicit functions of two variables. Consider f of x comma y equal to 0, which defines implicit function y of x. Here f is a function of x and y is a function of x. So if I try to draw a tree diagram for this, it will look like this, where f is a function of x and y is again a function of x, where x can always be written as a function of x. Therefore, differentiation of f with respect to x by chain rule can be written as f by x into dx by dx plus f by y into dy by dx. But dx by dx is 1 and f by x is 0 because f of x comma y is equal to 0. Therefore, its differentiation with respect to x is again 0. Therefore, LHS becomes 0. Here I wrote f by x as fx and f by y as fy. Rearranging the terms, we get dy by dx is equal to minus fx upon fy. This is how we can differentiate implicit function y of x. Now let us see example for this. Here we have to differentiate y with respect to x, where y is an implicit function of x given the function x square plus xy plus y square minus 8 is equal to 0. Let us see the solution. We let f of x comma y is equal to x square plus xy plus y square minus 8, which is RHS of the equation. Now we differentiate f partially with respect to x. It is equal to 2x plus y. Similarly, fy can be calculated. Therefore, by the formula of differentiation of implicit function, dy by dx is equal to minus fx upon fy. Substituting values for fx and fy, we get minus 2x plus y whole divided by x plus 2y. Let's go for example number 2, which is similar to example number 1. Here once again we have to find out dy by dx for the function y log cos x is equal to x log sin y. In the solution, we let f of x comma y as y log cos x minus x log sin y. Now we calculate what is partial derivative of f with respect to x. It is simply y into 1 by cos x minus sin x minus log sin y. Simplifying this, we get minus y tan x minus log sin y. Similarly, fy can be calculated, where fy is partial derivative of f with respect to y. By the formula of partial derivative of implicit function y with respect to x, we get minus of minus y tan x minus log sin y whole divided by log of cos x minus x cot y. Now let's go for example number 3, which is different than example number 1 and 2. Here u is given as x log xy and the another function x cube plus 3xy plus y cube is equal to 1 is also given. Question is to find out du by dx at a particular point 1, 1. In solution, we write the given part. Here u is equal to x log xy is given. So if I try to draw a tree diagram, it is clear that u is a function of x and y, and from the another equation which is mentioned in the question, y is a implicit function of x. Therefore in this tree diagram we can mention y as a function of x and x is always a function of x. So this completes the tree diagram. Now we write formula for du by dx. It is du by x into dx by dx plus du by y into dy by dx. Substituting values in this RHS part, more simplification will give us du by dx as log of xy plus 1 plus x by y into dy by dx. We label this as equation number 1. Now we let f of x comma y as x cube plus 3xy plus y cube minus 1, which is obtained from the second given equation from the question. We differentiate f partially with respect to x and partially with respect to y. From this data we can find out what is derivative of y with respect to x. By the formula it is minus fx upon fy. Substituting values for fx and fy, we get dy by dx as minus 3x square plus 3y whole divided by 3x plus 3y square. Now substituting this value of dy by dx in equation number 1, which is du by dx is equal to log of xy plus 1 plus x by y into dy by dx, we get log of xy plus 1 minus x by y into 3x square plus 3y divided by 3x plus 3y square. At a particular point 1, 1, du by dx becomes 0. Now these are some practice examples which you can try at home. If you like my video, please subscribe my YouTube channel given in this link. Thank you all.